Hey there, this is the matter and change portion of Unit 1 notes. So let's get started. First of all, matter is anything that has mass and takes up space. This is an old definition. You guys heard this a long time ago. And what you need to remember is you matter. Get it? You have mass and you take up space. I thought it was. So what are three things that you can think of that would not be classified as matter? So the first thing most kids say is air. Air is actually matter because the gases that make up air have a mass and they take up a lot of space, as much space as you'll give them, as a matter of fact. But basically anything with a wave, anything that's a wave is not matter. So things like light, sound, and heat are not matter. They're waves. Other waves would be radio waves, maybe the visible light portion of the spectrum, the waves that you can see. But again, don't get tricked. Air is definitely matter, and so we consider that to be matter. There's three basic states of matter. You know those three states of matter. They're solids, liquids, and gases. Solids have a definite shape and a definite volume, like your desk. Your desk has a definite shape and a definite volume. It doesn't change. Liquids, the shape can change, but it still has a definite volume. So if I take my water bottle that has half a liter of water in it and I pour it into a coffee cup, the shape has changed, but the volume of water hasn't changed. So liquids, shape can change, but not the volume. Gases can change shape and volume to match their container. They are in constant random motion. The next slide, what we wanted you to do was just draw a picture of the arrangements of the three states of matter, and you have a spot on your notes that you can do that. You can pause to do that. Matter can change from one state to another. There are 6 possible state changes, and you're going to need to know all of these 6. For each one, energy is either going to be absorbed or released in order for that substance to change state. So here are the 6 state changes. Freezing, you do know what freeze means. Sublimate may be a new one. When something goes from the solid state directly to a gas state, it skips the liquid phase. That's called sublimation. And dry ice is an example of a substance that sublimates. If you put dry ice out, you see it gives off that creepy looking fog. Well, it's really not fog. It's just turning into a gas, and it skips the liquid phase. So frozen carbon dioxide is one thing that sublimates. Condensation, you know what condensation is. On the outside of your windows in the summertime, if mom and dad have the air conditioner really cold in the house, the windows will be cold, and when the water vapor in the air touches the cold window, they'll condense and turn into liquid water on your window. So that's why it looks like your windows are sweating. You know what number 4, melting, is, going from a solid to a liquid. Evaporation, you also know what that is. If you leave your dog's water bowl out on the porch, you come back in a day or two, that water's going to be gone. It evaporated. It turned from a liquid to a solid. I'm sorry, from a liquid to a gas. And then deposition is when you freeze carbon dioxide, it goes directly from a gas to a solid. It skips the liquid phase. Physical changes are reversible. They're things that you can undo. Okay, that's how you know it's a physical change. You can reverse it and get back whatever you started with. All state changes are physical changes. That's important. That's a way to remember it if you're asked a question about whether something's a physical or a chemical change. If it's a change in state, if it's a phase change like evaporation or freezing, those things are physical changes because you can always turn them back. If I freeze a cup of water, put a cup of water in the freezer and it turns to solid ice, I can get the liquid water back. All I have to do is take the glass out of the freezer and leave it on the counter, and that will turn back into a liquid. Dissolving is kind of tricky. It is a physical change. If I dissolve salt in water and stir it up really good, it looks all the same. It looks like the salt has disappeared, but it hasn't. If I heat up that water or allow the water to evaporate, I'll be left with the salt, so I can get my salt back. Last, shape changes are physical changes. That means, tearing a piece of paper in half is still paper. It's just now two pieces of paper instead of one. So chemical changes produce something totally new. They produce a new substance. The new substance will have different properties, definitely way different than what they started as. The ways that you know that a chemical change has occurred, well, this is 4 evidences of a chemical change. There's a lot of them, but these are 4 big ones. So color change indicates a chemical change has occurred. If the leaves fall off the trees in the fall and turn brown, that's a permanent color change. They're never going to be green again. Bubbles in the formation of gas, bubbles will appear. So anytime that I put a metal in an acid, it will give off hydrogen gas. So it will look like it's bubbling. So that's what it's doing. Number 3, a new solid may form. So when there's a neat experiment that we can do, a lab that we can do in class, where we mix together 2 very specific clear liquids. When we mix them together, we get a colored solid powder. So that's very magical, and it's called a precipitate, and that's one evidence that a chemical change has occurred. Also, there may be a temperature change. If bonds are breaking or bonds are forming, you may have an exothermic or an endothermic reaction where something will feel hot or cold. Chemical changes are also called chemical reactions. Chemical reactions always produce something new. Rusting is a chemical reaction. You have metal, and if you leave it outdoors long enough in the air and the water, it will rust, and you can never get that metal back to the way it was. That metal's permanently changed into rust. Things like cooking. Cooking is a chemical change. If I put eggs and flour and sugar and butter together and stir it all up and put it in a pan and put it in the oven and make a cake, once I have that cake, a chemical change has occurred, and I'm never going to get my eggs back or my sugar or anything else. So a chemical change has occurred. Properties of matter. A property is something that you can observe or something that you can measure. And there are 2 types of properties. There are both physical properties and there are chemical properties. Physical properties can be measured or observed without changing or destroying the sample. For example, if I put something on a scale, I can measure its mass. I can see its mass, I can observe that mass without changing the substance at all. Malleability is an example of a physical property. If I have a piece of metal and I bend it and shape it into a different shape, well, I still have that same metal. I haven't changed anything. All I've done is change its shape. So it doesn't change it chemically. So these are some examples of physical properties. Within those physical properties, there are 2 types of physical properties. There are extensive properties and there are intensive properties. Extensive properties depend on the amount of substance that's present. So if I gave the example in class, if I take myself and I stand on a bathroom scale, I can measure my mass. If I pick up my granddaughter and step on that bathroom scale, I have a different mass. Okay, mass is something that depends on the amount of substance present. If, for example, I take a piece of notebook paper, it's 8.5 by 11 inches. If I tear that piece of notebook paper in half, I now have 2 pieces of paper that are 8.5 by 5.5 inches. Okay, in that case, length depends on the amount of substance. So those are extensive properties. Intensive properties stay the same no matter how much you have. So let's say I have an orange piece of construction paper. If I have an orange piece of construction paper and I cut up that orange piece of construction paper, it's still orange. It doesn't matter how small the pieces are, it's still orange construction paper. If I decide I'm going to boil water for, let's say for instant oatmeal, I take a half a cup of water, I put that on the stove and I heat it up to boiling. Boiling is 100 degrees Celsius. The water has to get to 100 degrees Celsius in order for it to boil. So let's say I'm going to make spaghetti that night. and I take 2 quarts of water, not half a cup anymore. I take 2 quarts of water. I put that in a pot. I turn it on the stove, and I turn it on and heat it up to boiling. What temperature does it have to get to boil? Right, it has to get to 100 degrees Celsius in order to boil. No matter how much water I have, it's going to boil at 100 degrees. That's an intensive property. It doesn't matter how much you have. It's always the same. Chemical properties are how a substance reacts with other substances. Let's see. Chemical properties can't be measured and they can't be observed without changing or destroying the sample. So I'm not going to be able to observe whether or not something's flammable unless I set it on fire. Or once I set it on fire, that stuff's going to be completely destroyed and changed into something else, like a pile of ash likely. These are easy to recognize and they always react. So if you're trying to identify whether or not a property is chemical or physical, if you see the word react or reacts or reacting, it's chemical. Examples of chemical properties include reactivity, just like I said, flammability, whether or not something will catch fire, combustibility, whether or not something can explode or be spontaneous in its ability to burn, whether or not something oxidizes, its ability to react with air or to rust. There's a lot of different oxidizing. Or whether or not something's corrosive, if it reacts with an acid or if it reacts with a base. These are all examples of chemical properties. There are two types of matter. There are pure substances, which are elements and compounds, and there are mixtures. Matter can be broken down in this flowchart. It's a really neat flowchart. I think it helps a lot. It can be broken down here, as you see, into mixtures and pure substances. If something is determined to be a mixture, it's either going to be a heterogeneous mixture or a homogeneous mixture, and we'll talk about what both of those mean in a minute. If it's a pure substance, then it's either going to be a compound or an element. Compounds can be broken down by some sort of chemical process, some sort of reaction. Elements can't be broken down any further. Elements are what they are. If something is an element, it will have its very own block by itself on the periodic table. Okay, so it would be an example of an element would be hydrogen or copper or xenon. Those have their very own space on the periodic table, and they never change. Pure substances, this flowchart, I'm not as fond of it, but pure substances can be broken down into elements or compounds. Here, if you follow the flowchart, it says, does it consist of different types of atoms? Well, if it doesn't, then it's an element on the left. Does it consist of molecules? Molecules are atoms that don't exist alone. There are just a very few of them, and chlorine is one example. Chlorine doesn't exist as just Cl, just a one chlorine atom. It always is bonded to either another atom, some other compound, some other element, or it's bonded to itself. It just can't be alone, so it's always Cl2. There's always two of them together. If it doesn't consist of molecules, it's just an atom, like in this example, argon, just a plain old atom by itself. It can't exist alone. Back to pure substances. If it consists of different types of atoms, then over on the right, it is a compound. Does it consist of molecules? Well, if the answer is no, then it's a formula unit. Formula units are the names, is the name that we give to compounds that consist of a metal and a nonmetal. Sodium chloride is a metal bonded to a nonmetal. Sodium is a metal and chlorine's a nonmetal. If it does consist of molecules, molecules are the names that we give to compounds that have just nonmetals bonded together. In this case, H2O, or water, is the example molecule, and hydrogen is a nonmetal, and so is oxygen. Elements, individual elements can't be broken down. They are as simple as they can possibly be. You can't break them down by normal chemical means. They are found on the periodic table. They'll have their very own box. They're found as single atoms unless they are, like I said before, they're diatomic. They're the ones that can't exist alone. Some gases exist as two atoms bonded together. We use the word Brinkelhoff so that we can remember which elements are diatomic. Brinkelhoff spells, using the elements themselves, spells out that strange word made up of all the diatomic elements. So Br is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All of those atoms don't exist alone. They'll always have a subscript of 2, meaning there will be 2 bonded together. Or they may be bonded to another element, like bromine chloride, or I'm sorry, bromine and sodium might be bonded together. As long as they're not alone, that's the important part. Compounds can be broken down by chemical reactions. They're going to be made up of 2 or more elements that are chemically combined and they're bonded together. They'll have a formula that doesn't change. The formula will be the same all the time. The compound will have new properties, and these properties are not the same as the elements that make up the compound. So for instance, here we have sodium metal on the left. It's silvery. It is a metal, kind of soft. Sodium is an explosive. It explodes in water. It explodes in water. It's very flammable when it comes into contact with water. It's pretty dangerous. It's a pretty dangerous metal. You have to keep it way away from water. Next to that is chlorine gas. Chlorine gas is very, very corrosive. It can be poisonous. It's toxic. You don't want to get into contact with chlorine gas. But when you mix those two fairly dangerous elements together, you get table salt. And we all know that table salt does not explode in water, nor is it highly corrosive. It can be, but not as much as chlorine gas. So the point here is that the compound that's made, the table salt, doesn't resemble the elements that make it up. Those properties are different, very different in this case. Examples of pure substances include carbon, oxygen, gold, neon. All of those are elements, and they'll have their very own box on the periodic table. Compounds have a formula. Water is H2O, sodium chloride, hydrogen peroxide, methane, and glucose. If it has a chemical formula, then it is considered to be a compound. Okay, some example problems here. A substance that cannot be separated into simpler substances by physical or chemical means is what? Yep, it's an element, B. Number 2, a chemical combination of 2 or more different elements is called what? Yep, it's called a compound. Which of the following is an example of an element? Well, copper is the only one that's an example of an element, and that's letter A. Which of the following is an example of a compound? Well, what you're looking for is 2 or more elements combined. You're looking for a formula, and the only formula up there is the one for water, H2O. Okay, mixtures. Mixture is a physical combination of 2 or more pure substances. A mixture can be separated by physical means, and there are several physical means that we're going to talk about. The components of the mixture retain their original properties. They keep their same properties. If we mix salt and water and we heat up the saltwater solution and evaporate the water, water keeps its same properties. It's still water. And the salt will have its own properties also. They retain their original properties. They're not changed permanently. Examples of mixtures include salt water, like water and salt, sugar water, pouring sugar into water. Air is an example of a mixture. Yes, it is. It's made up of nitrogen, oxygen, some carbon dioxide, some argon, lots of different stuff. Brass is called an alloy. Brass is a mixture of metals. It's a mixture of copper and zinc. Okay, so these are examples of elements, compounds, and mixtures particle diagrams. Look through them. Most of them are fairly self-explanatory. I think, let's see, mixture on the bottom right, the mixture of elements and a compound, you can tell that one's a compound because the atoms that are bonded together are different in color. They're green and purple. The two blue ones together, those would be molecules. Those would be diatomic molecules, one of the Brinkelhoff atoms. And the red would just be an example of a plain old atom. There's two types of mixtures. There are homogeneous mixtures, and homo is Greek for the same. It means the same. It has a uniform appearance, meaning it looks the same throughout. These are also called solutions, and you do need to know that. Homogeneous mixtures are called solutions. There are also heterogeneous mixtures. Heterogeneous mixtures don't have a uniform appearance. They'll not look the same throughout, like that trail mix doesn't look the same throughout. Lucky Charms is my favorite mixture, my favorite heterogeneous mixture anyway. Mixtures can be broken down into either heterogeneous, meaning they're all mixed up, or homogeneous, having a uniform appearance. Mixtures can be separated. We can separate them using physical means. There's some physical means below. Filtration is one. You separate components based on their size. So if I have a mixture of sand and water, I can pour the sandy water through a filter, and I can collect the sand on the filter, and the water will go through as filtrate. Distillation is a way to separate components based on their different boiling points. If I boil a mixture of alcohol and water, the alcohol has a lower boiling point, so it will start to boil first. So I can separate those two mixtures based on their boiling points. And chromatography separates things based on their differences in solubility. Now, we did chromatography, if you remember, in class. So I think there's some pictures in a minute. Chromatography. This is filtration. Looks just like you would expect. There's a funnel, filter paper. You filter, the liquid goes through, the solid stays on the filter. Not a whole lot crazy. It's just like you would expect filtration to be. Distillation. This is a distillation apparatus. On the left, if you heat up that mixture of water and alcohol, the alcohol will start to vaporize. When it does, it will rise, and those vapors will go through the condenser or the condensing tube that's in the middle. In that condensing tube, the vapors of alcohol will cool off. When it does, it cools off and condenses into liquid alcohol on the right. So you can see the receiving flask is collecting that alcohol that would be boiled off, and the water would still be present in the flask on the right, or I'm sorry, on the left. An example of chromatography, the chromatography that we did in class, we used round filter paper, but it's the same basic thing. You can separate based on differences in solubility. This would probably depend on how well mixed it is. If you wanted to separate out, that should say out the colors in a black marker, how could you separate them? Right, you would use chromatography, exactly what we did in class. Example 3, if you wanted to separate sand and water, what would you do to separate them? Well, I talked about that a little bit earlier. You'd use filtration. Examples of mixtures. Homogeneous mixtures will have a similar appearance throughout. Air is homogeneous. It has a similar appearance throughout. Heterogeneous things, on the right, there's pictures of granite, salad, soil. Those things are, if you look at them closely, they'll have different parts throughout. They're not uniform in their appearance. Okay, is this homogeneous or heterogeneous? Salt water, well, has a uniform appearance, so I'm going to go with homogeneous. How about this mixture? Homogeneous or heterogeneous? Yep, heterogeneous. Homo or heterogeneous? Homogeneous, has a similar appearance throughout. What do you think, homogeneous or heterogeneous? It's heterogeneous. Clearly, this has a different appearance throughout, so this is heterogeneous. brass. Well, brass is a mixture of metals, but when you look at that trumpet on the right, does it look like it's similar throughout? It sure does to me, so I go with homogeneous. How about this? Pure gold. Homogeneous or heterogeneous? I got you. It is not homogeneous. It is a pure substance. Pure substances are not categorized as heterogeneous or homogeneous. So that was kind of tricky. Well, I hope that this video helped you, and pause me, rewind me, ask questions in class of your teacher if you need to.